Welcome! So we're going to resume our geometric thinking exercises. So the first question here that we'll do is question 7. Find the vector and scalar equations of the plane through, let's say, a point P equal to -1, 6, -5, parallel to the plane x plus y plus z plus 2 equals 0. So we've got to find this plane. It's parallel to this one and it passes through this point. Okay, so looking at this, let's just sketch a little picture. We've got a normal vector, right? And now that normal vector can be obtained from looking at the coefficients of the scalar equation of this plane. So n equals 1, 1, 1. All right, now if we have a parallel plane that contains the point P, so what would be the scalar equation of that, of this plane here? Well, it's pretty easy because it has the same normal vector, given that it's parallel. Okay, and so that means that it looks like x plus y plus z is equal to d, and we don't yet know the value of d. However, we do have this point that is on this plane. So since P is on this plane, we have -1 plus 6 plus -5 is equal to d, and so that tells us d, doesn't it? So here then, 6 minus 5 is 1, 1 minus 1 is 0, so d is equal to 0, and then this plane is x plus y plus z equals 0. All right, so we've got the scalar equation of that plane. What about a vector equation of that plane? Okay, so for a vector equation, let's just take some other point here, x, y, z, and we'll call it q. Okay, and consider the vector from P to Q. So the vector from P to Q is the vector PQ, and we can find that by taking the coordinates of Q, subtracting the coordinates of P, or in other words, the vector Q from the origin to the point Q, and the vector P from the origin to the point P, position vectors. All right, and so what this is then is x, y, z minus -1, 6, -5. Okay, so we have x minus -1 is +1, y minus 6, z minus -5, so +5. All right, and let's give this a name, lowercase r. So lowercase r is this vector, and it is parallel to the plane. So that means then that the normal vector n is perpendicular to the vector r. So since n and r are perpendicular, I'll just put perp for short, then n dot r is 0. The dot product is 0 because they're perpendicular vectors. So what this says then is that 1, 1, 1 dot x plus 1, y minus 6, z plus 5 is equal to the 0 vector, and when we dot that out, well, we just get this, right? Because think about it, 1 times x plus 1 times y plus 1 times z is x plus y plus z. 1 times 1 plus 1 times -6 plus 1 times 5, well, that gives us 0. So we just get this. So you could consider this right here to be the vector equation of the plane. but there's also another vector equation of the plane. All right, and so they look more like what we have in question 9, but in question 9 we have some lines. So I want to start by talking about those lines. So let's just jump into question 9. And so in question 9 we have two vector equations of lines in 3D. And you could think of this as a parameterization of these lines in 3D. So this is a vector, and lambda in this case is any real number. Right? It gives you a description of points, but I'll talk about that in a moment. So we have R1 is that. Now R2 is 202 plus mu minus 1, 1, 0, where mu is any real number. Okay, now R1 is the vector from the origin O to a point, uppercase R1, right, where this, because this is O, will have the same coordinates as what the vector does. So remember, that's R1 minus O. And so since O is 0, 0, 0, R1 being just, the coordinates of this, so it does give us a description of points, because this, you could take this to be a point, right? Okay, so let's see. Consider when, say, lambda is equal to 0, what do we get? Well, R1 would be equal to just 1, 1, 0. So the point 1, 1, 0 is on the first line. Okay, now if we choose a different value of lambda, we get a different point on that line. So if lambda is equal to 1, well, then we get R1 equal to, now if that's 1, we're just adding 1 plus 1 is 2. 1 minus 1 is 0. 0 plus 2 is 2. Okay, I think I accidentally solved that problem too, because it asks us where they intersect. But so when lambda is equal to 1, we get this. And so 2, 0, 2 is also a point on the line, the first line. Okay, so when lambda is equal to 1, mu is 0 if these lines intersect. But the way that we solve an intersection problem like this, when we're given two parameterized lines, is to look at these and solve for when the parameters are equal. All right, so to find an intersection, solve for the parameters lambda and mu such that they give the same point. Okay, so let's go ahead and do that. So we would have 1, 1, 0 plus lambda 1 minus 1, 2 equal to 2, 0, 2 plus mu times minus 1, 1, 0. Okay, now expanding these, so expanding the left-hand side, we'd have lambda for the product of those, and then plus 1, comma, minus lambda, and then plus 1, and then 2 lambda plus 0. And so over here, expanding, we have 2 minus mu, and then mu times 1 is mu plus 0, and then mu times 0 is 0 plus 2 is just 2 there. Okay, so this gives us three scalar equations matching these components up. So the first equation would be lambda plus 1 is 2 minus mu, The second equation, minus lambda plus 1, is mu. And the third equation is 2 lambda is equal to 2. Now that third equation tells us the value of lambda straight away. So we've got lambda equals 1. Now if lambda is equal to 1, we sub that in here and we've got mu equals 0. Okay, so these two equations here gave us values, but we do need to check that they're consistent in here, because if they're not consistent there, then those lines actually don't intersect. They give us a contradiction to the assumption that they intersect. Okay, so checking 1 plus 1 is equal to 0. Hang on, is that right? I better double check this. Okay, lambda plus 1 minus mu plus 2. 2 minus mu. No, 1 plus 1 is 2. What am I thinking? Of course. Okay, good. And that's equal to 2 minus 0. So this checks out. So yes, they do intersect, and they intersect when this happens. Okay, so now let's find the actual points of intersection. So we can take either one of these. So if we just take this one and sub it into the second equation, so when mu equals 0, we get R2 is equal to 2, 0, 2, which gives us the point of intersection, right? This is the point of intersection of these two vector equations of those lines. All right, and if you want to visualize this, you can think of these like, get a mate and a piece of string, and you and a mate hold a piece of string, separate so that the string is taut. All right, and then maybe you can visualize a line in 3D. Okay, let's look at question 10 here. Show that the curve of intersection of the two surfaces, so I'm going to write them on top of one another, or one above the other. So there's one surface. Then the other surface, 2x squared plus 4y squared minus 2z squared minus 5y is 0. Is this correct? All right, looks like that. This, yep, okay. So we've got to show that the curve of intersection lies in a plane. All right, so the technique we would want to use here is to eliminate one of the variables. Is there any easy way to do this? Well, yeah, look, the z's are fairly similar. We just need to multiply the first equation by 2 and then subtract. So let's do that. 2x squared plus 2y squared minus 2z squared plus 6x equals 2. 2x squared plus 4y squared minus 2z squared minus 5y is 0. All right, so subtracting these, well, some things vanish, right? So which way do I want to go? Probably second equation minus first, so that this one, difference of these two gives a positive number. Okay, so second equation minus first equation, the x squareds vanish. We've got 2y squared. These vanish. So this minus this is minus 11. Oh no, they're not the same term. Okay, so minus 5y minus 6x equals minus 2. Let's double check. This minus this 0. This minus this 2y squared. This minus this 0. This minus 5y minus 6x. This minus 2. Okay, good. Now we've got to show that that occurs in a plane. All right. Because that looks like a parabola, doesn't it? Oh, I see. I've done something wrong there. That should be a 4, because when I multiplied by 2, I didn't multiply this by 2, did I? So these actually vanish, and that's not there. Okay? All right, so this is the difference. Yeah, that's in a plane. And that's that question done.